Hello, welcome to our electronics education program. I'm Vincent Chang. We're going to continue our lecture series on the subject of MOSFET. MOS field effect transistors, MOSFETs, Part 3, Physical Operation. Let's review a few concepts we talked about before. Number one, the threshold voltage. The threshold voltage. Basically, the MOSFET, the N-channel enhancement MOSFET, is a normally off device. If we don't apply any voltage on the top, on the gate, then there's no current, there's no channel. If we apply a VGS is greater than VT, VGS is greater than VT, then the channel will be formed. The N-channel will be formed between source and the drain. Once the channel is formed, then the current ID is controlled by the concept of field effect and the voltage control. The ID will be controlled by VGS and the VDS. ID will be controlled by VGS and the VDS based on the concept of field effect. Now, this lecture, we are not going to do any mathematical derivation and going too deep, but I want you to use a very simple way to help you understand the current voltage characteristic of the MOSFET based on 6 points. 6 points. VGS, each point is a combination between a specific VGS and the VDS. See, on the top is the VGS, the value of VGS. On the bottom is the value of VDS, for example. The point D, VGS, is the combination of VGS, 5 volt of VGS and the 2 volt of VGS. VDS, point D corresponds to VGS equals 5 volt and the VDS equals 2 volt. Let's start with the point 8. When VGS equals 5 volt and the VDS equals 0.1 volt. When VGS, look at the slide, equals 5 and the VDS equals 0.1. Let's start with the VDS equals 0.1. What does that mean? You can just neglect the very small difference between the drain voltage and the source voltage. For the voltage across the VGS, gate, and the source is 5 volt. What about gate and drain? 5 minus 0.1, so 4.9. In other words, in this case, in this situation, the channel is kind of symmetric. The source and drain is kind of symmetric. 5, 4.9. The left-hand side is 5 volt, and the right-hand side is the 4.9. So the channel will be what? It's kind of uniform. It's kind of a uniform distribution. There's a little difference between the drain side and the source side. But if we neglect the 0.1, the difference is kind of the uniform distribution. So uniform represent what? The uniform distribution of the channel represent the linearity. The linearity between the ID, the current, and the voltage VDS. The linearity between the ID, the current, and the voltage. In other words, the behavior of this device at this point is kind of similar to what? To a linear resistor. Follows Ohm's law. Basically follows Ohm's law. So ID will be linearly related to the voltage VDS. The slope represents the inverse of the resistance. The resistance corresponds to the inverse of the slope. Here's the point A. What about the point B? The VDS is the same. The linearity remains the same. The symmetry between source and drain uniformity of the channel remains the same. And then the VGS is reduced, is decreased. Means what? Remember, the vertical electric field is going to become weaker. Then the surface electron concentration will be lower. In other words, the channel depth will become smaller. The resistance will become higher. The slope will become lower. The current will be reduced. The slope will become lower. The current will be reduced. So from A to B, 5 to 3, A to B. So what about when VGS equals VT? Let's assume the threshold voltage of the device is 1 volt. Then it's just between the on and off. Let's neglect the very small current when the channel is barely on. It's just turned on. Then the ID is almost 0. So 5, 3, 1, 0.1, 0.1, 0.1, VGS 5, 3, 1, and then A, B, C. In other words, for these 3 points, the combination of this A, B, C tells us the behavior of the device around the origin. Around the origin of the IV curve is voltage control resistance. The behavior of the device is similar to a resistor, and which value, the resistance value, is controlled by what? By VGS, voltage control resistor. Let me repeat that. The behavior of the device, when VDS is small, the behavior of the device is similar to a resistor, but which value is controlled by VGS. The behavior between source and drain is like a resistor, but which value is controlled by the third terminal, the gate terminal. Now let's move on to the right-hand side, okay? Another 3 point, D, E, F. Let's analyze this device qualitatively. VDS, let's keep the VDS the same, the 5, 5, 5, but gradually increase VDS 2, 4, 6. All right? 5, 2, 5, 4, and then 5, 6. So let's start with the point D, 5, 2. When VDS equals 5 volt, for the D point D, VGS is 5 volt, and VDS is 2 volt. Then on the left-hand side, look at the device. On the left-hand side, 5 minus 2 equals 3. No. On the left-hand side. Sorry. On the left-hand side, 5 minus... What am I doing? 5 minus 0 equals 5. So on the right-hand side, 5 minus 2 equals 3. So along the channel, 2, 1, 0. So 5, 4, 3. I'm talking about the voltage drop across the MOS structure along the channel. So from source to drain, the voltage drop is getting smaller and weaker, and the channel is become kind of taper and become shallower. This kind of structure tells us the linearity is broken. So the current is kind of going downward. The increase is kind of a little bit difficult. It's kind of going downward. It's kind of been limited. Then this is the point D. Point D correspond to VGS equals 5 volt. Let me take out this. VGS point D correspond to VDS equals 5 volt. And VDS equals 2 volt. So 5, 2. What about the point E? When we get to the point E, VGS is the same. Let me go back. VGS is the same. It's still 5 volt, but VDS increased 4 volt. remember, we assume the threshold voltage is 1 volt. So look at the device. The right-hand side now is 4 volt. So the corner of the right-hand corner of the channel, what's the voltage drop across the MOS? 5 minus what? 4 equals 1. So 1 equals VT, means pinch off. Means it's the barely on. It's the pinch off. The channel on the drain end, at the drain end, is got pinch off. So this is the pinch off point. So point E is associated with the channel at the drain end got pinch off. Now let's move on to the last point, point F. 5, 6. When VGS equals 5 volt and VDS equals 4 volt or 6 volt, then 6, 5, 4. I'm talking about 6, this is 6, the drain end 6, and 5, 4, 3, 2, 1, 0. There is source, okay? So look at the 4. 6, 5, 4. So 4 is the pinch off point. Because at 4, the channel voltage, channel potential is 4. 5 minus 4 equals 1, right? Pinch off point. So pinch off point, beyond the pinch off point, if we keep increasing the VDS, then the pinch off point is going to move leftward. Then the device enters into another region we call saturation region or pinch off region. Ideally, in this case, the current cannot be increased. Ideally, in this region, the current will be saturated. The current will be saturated. Again, phi 2, point D, phi 4, point E. Let's go back. Phi 2, 3. I'm talking about phi minus 2 equals 3, right? VGD. G, the difference between gate and drain. Gate and drain. Gate, phi, and drain. Let me pull out my video. 2. So 3, okay. GD, VGD. Look at the slide. VGD. 3 is greater than 1. 3 is greater than 1. VGD is greater than VT. Trial region. Trial region. And then what? Then point E. VGD equals VT. Phi 4. Phi minus 4 equals 1. 1 equals 1. VGD equals VT. Boundary. Boundary. And then saturation. GD. Phi minus 6. Negative 1. Is less than 1. Alright? Saturation. Let me repeat. From left to the right, trial, boundary, saturation. 3, let's try to make this easier, right? It's greater than 1, trial. 1 equals 1, boundary. Negative 1 is less than 1, saturation. Trial, boundary, saturation. 2 inequality and 1 equation. The second type of representation. The second representation scheme to describe the 3 conditions, trial, boundary, and saturation. Here's another one. The inequality, which is to tell us 2 is less than 5 minus 1. Do you understand what I'm saying? VDS 2, right? VDS is less than VGS minus VT. VDS is less than VGS minus VT. 2 is less than 4. 2 is less than 4. Now boundary, 4 equals 4. 4 equals 4. VDS equals VGS minus VT. 4 equals 4. VDS equals VGS minus VT. The right hand side. And then 6 is larger than, is greater than 4. VDS is greater than VGS minus VT. We have come to the end of this lecture. The takeaway, I used the number one. I used the 6 point to elaborate, to explain qualitatively how the MOSFET works, where the current voltage characteristics comes from. Qualitatively illustration of the current voltage characteristic. A family of curve between ID and VDS corresponds to pertaining to associate with different what? Different what? Different VGS. The relationship between ID and the VDS is the family of curve associated with the different VGS. Key point number 2. VGD is greater than VT, trial, boundary, the saturation. The VGD is less than VT. The first representation scheme to represent the 3 conditions. The final one, the final takeaway, another representation to represent the 3 conditions is VDS, the relationship between VDS and the VGS minus VT, which is what we call overdrive. The driving voltage VGS is the part of the driving voltage over the VT. The VGS minus VT is the overdrive. So VDS on the left-hand side, the trial region, VDS less than overdrive, equals overdrive, and VDS is greater than overdrive. So we have come to the end of the lecture. Thanks for watching.